In the first lecture on kinematics of nuclear reaction, we have discussed the general non-relativistic formula for the Q value of the equation. Now today we will see the solution of that very equation and get the more informations regarding the nuclear reaction kinematics. For your convenience, I have just mentioned here the important results of the first lecture on this chapter. So you can see we have assumed that there is a stationary target nucleus denoted by this symbol capital X, which is bombarded by a projectile denoted by this symbol small x. And after the reaction, the product is the nucleus denoted by capital Y and a particle emerges which has been denoted by this small y. So this capital X denotes the target nucleus, or you can say the parent nucleus. A small x denotes the particle which is bombarded or incident on that. That is, you can say the projectile particle. And this capital Y is the daughter nucleus and a small y is the emerged particle. So we have taken this nuclear reaction and considered that the particle is scattered at an angle theta, and the recoil nucleus recoils at an angle phi to the incident direction. This was our fact of the first lecture on this chapter. Then we have defined the Q value of that equation. You have seen that the Q value is defined as the difference of the kinetic energy of the products of the reaction and the reactants of the reactor. So you can see this EY, E capital Y, subscript is capital Y. This denotes actually the kinetic energy of the recoil nucleus, and E subscript a small y, this denotes the kinetic energy of the emerged particle, and EX denotes the kinetic energy of the incident particle. So EY plus this EY minus EX defines the Q value of the nuclear reaction. Now when we have considered the total energy, which includes actually the rest mass energy and the kinetic energy, then we have got another expression for Q value, and that expression was Q equal to mx, capital MX plus a small mx minus capital My plus a small my into C square. You know, in this notation, this capital MX is actually the rest mass of the target nucleus, and a small mx, this is actually the rest mass of the projectile. This capital My denotes the rest mass of the recoil nucleus, and a small my denotes the mass of the emerged particle. And then after solving these two equations, we have got actually the non-relativistic expression for the Q value of the reaction, eliminating the term phi in terms of EY and EX. EY means kinetic energy of the emerged particle, and EX is kinetic energy of the incident particle. This expression defined in D does not contain the kinetic energy of the recoil nucleus, which is actually very small and very hard to measure. So this expression Q, which is called in fact kinetic equation or non-relativistic kinetic equation, is Q equal to EY into 1 plus My over capital My minus EX into 1 minus small mx by capital My minus 2 over capital My into a square root of mx, my, ex, ey into cos theta. You have seen that this theta is simply the angle at which the particle emerges from the incident direction. So these were the results. Now in this lecture, our aim is to find the general solution of this equation D, which is actually the non-relativistic expression for the Q value of the process. So we will see its general solution. So now let us see the general solution of this equation. So for the general solution, you can see the form of equation D, and from this form it is possible to express this equation for a fixed value of Q as a quadratic equation in terms of root over Ey. So how we can change this equation in the form of a quadratic equation in terms of root over Ey for a given value of Q? First of all, we will see it. And for this, to express equation D as a quadratic equation, in root over Ey, we have from D. We can rewrite actually D in this manner. You have seen that this Q is equal to 1 plus a small my by capital My into E small y, and this, taking the minus sign common, it may be written as plus mx over capital My minus 1 into Ex, and minus 2 over My square root of mx into My into Ex into Ey into cos theta. This is just equation D. I have just written the same equation. Now let us take in RHS the LCM, and that LCM will be actually My, and you can multiply it by My in LHS. So you can write this as Q into My, or you can simply say we multiply this equation both sides by My. So what will be the result after multiplying by My? You can see this will be actually equal to My plus a small My into Ey, and plus mx minus My into Ex, and minus, here My will cancel out, this will be minus 2 a square root of mx into My Ex into Ey into cos theta. This is cos theta. Now let us rearrange the different terms in this equation, and you can see after rearranging that term, this equation may be written as My plus My into Ey, and minus 2 into root over mx into My into Ex into cos theta into root over Ey. I have just rearranged the terms, and minus q into my. Actually, I have brought this term qmy in another side, so this will become negative. I have taken the minus sign common here, so minus qmy plus my minus mx, as minus sign has been taken common, so here sign is just reversed, into Ex, and this equal to 0. Now you can see this equation. This equation is just in the form of what? This is in the form of ax square plus by plus c equal to 0. That is in the form of a quadratic equation, and you can compare from this quadratic equation to equation 1. In place of x there is simply root over Ey. So I have told you that this equation may be changed into a form of quadratic equation in terms of root Ey, and at the place of a this is my plus my, and at the place of b there is minus 2 root over mx my ex into cos theta, and at the place of c you can see this is actually minus qmy plus my minus mx into ex. So this is just a quadratic equation in terms of root over Ey. So we can find the value of root over Ey, that is the roots of this equation. So you can say it is a quadratic equation. Quadratic equation in root over Ey, and so its solution is given as, you know, the solution of a quadratic equation is simply x equal to minus b plus minus root over b square minus 4ac divided by 2a. So comparing the solution from the standard quadratic equation, we can write that root over Ey is equal to minus b, and you can see the value of b is minus 2 root over mx my ex into cos theta. So here will be minus minus plus, this will be 2 root over mx into my into ex to the power half into cos theta, and plus minus root over b square. What will be b square? This will be simply 4 into mx into my into ex into cos square theta, and minus 4ac. Since c is negative here, so this will be plus 4 into a. A is in fact my plus my. So this will be 4 my plus a small my, and into c, and c is what? You can see this c is minus this much. For that minus I have written here plus. So this will be into qmy plus my minus mx into ex and whole to the power half, and whole divided by 2a, and a is my plus my, so this will be 2 into my plus my. So this is the solution of this quadratic equation. Now let us divide each term of the numerator by the denominator 2 into my plus my. So after dividing by this denominator, what will be our result? You can see easily this will be simply mx root over mx into my into ex into cos theta over my plus small my, and plus minus, you can see when we will divide the each term inside this square bracket by 2 into my plus my, since the numerator is under the square root, so we will simply square the denominator and then take into inside the square root. So this will be what? This will be mx into my into ex into cos square theta and divided by my plus my. Here 4 factor is cancel out, and plus this will be qmy plus my minus mx into ex and whole divided by my plus my plus my, and a square root of this much. So you can see this root over ey is equal to this much. Now we can express this relation in a simpler form. You can write this expression as, therefore we can write root over ey is equal to p plus minus root over p square plus q, and say this is equation 1a. In fact, we have written this p and q instead of which quantity you can see it very easily. You can see the equation here and recognize the p and q. You can see that this p is simply root over mx my ex into cos theta over my plus my, and q is instead of qmy plus my minus mx into ex divided by my plus my. So what are the meaning of this p and q? You can see that p is written instead of root over mx into my into ex into cos theta over my plus my, and this q has been written at the place of this qmy plus my minus mx into ex divided by my this is in fact capital Y, My plus My. Let us say this is equation 2. So these are the values of P and Q. So you have seen that the Q value equation can be expressed as a quadratic equation in root over Ey. Now from this result, we can easily discuss the energetics of the nuclear reaction. So to deal with the energetics of nuclear reaction, let us discuss these results. Nuclear reaction. So actually, you know, like chemical reaction, nuclear reactions can be also of two types. We have already discussed these two types of nuclear reaction in first lecture on this topic. So just like chemical reaction, nuclear reactions are also of two types. And what are those two types? Actually, those two types are, first one is exoergic reaction. Exoergic reaction. You have learned that in case of exoergic reaction, actually the Q value of the reaction is positive. So in case of exoergic reaction, there is positive Q. And the second type of nuclear reaction is endoergic reaction. This is endoergic reaction. And you know, for all endoergic reaction, the Q value of the reaction is negative. So you can say for this there will be negative value of Q. So now we will discuss the energetics of these two types of reactions separately in detail. So let us start to deal with from the exoergic reaction. So number one is exoergic reaction. What is the kinematics of this exoergic reaction? Now we will deal with. Actually, you know, for this type of reaction, Q value is necessarily positive. And if the Q value is positive, then the reactions of these types can take place spontaneously, at least in principle. And when you say these types of reactions may take place spontaneously, what does it mean? Actually, it means that this reaction may be initiated even when the kinetic energy of the incident particle is 0. So we will first study the variation of kinetic energy of the emergent particle, that is the value of Ey, and their angular distribution too, as the kinetic energy of the incident particle is gradually increased from 0. It means we will take two conditions. First one will be 0 projectile energy, and another will be finite projectile energy. So you can say what are the main facts regarding this exoergic reaction? You can say that Q is positive for such reactions, and this reaction may be initiated spontaneously, that is, even when Ex, you know, this Ex is kinetic energy of our projectile. So when Ex will tend to 0 or Ex is equal to 0, you may say, even then this reaction may proceed. And so in this condition, we will study the kinetics of this exoergic reaction in two headings. First of all, we will consider that Ex is 0, and then we will consider Ex has a finite value. So let us now first of all consider the case of zero projectile energy. Zero projectile energy. Zero projectile energy. When you say zero projectile energy, what does it mean? It means the kinetic energy of the incident particle Ex, it tends to 0. So in this case, kinetic energy of the projectile tends to 0. And you can see from the expression for P, here there is expression for P, you can see this P is in fact directly proportional to a square root of Ex. So when Ex will be 0, you can see from this relation, this P will be also 0. So when we say that Ex is tending towards 0, it means we are saying that P is tending towards 0. So in this case, Ex tends to 0, and hence P tends to 0. And as P will tend to 0, then what will be the value of Q? Now let us see the expression for Q. The expression for Q, you can see from here that when Ex will be 0, this term My minus Mx into Ex will vanish, this will be 0. So Q will be simply Qmy divided by My plus My. So in this condition, we can say, so Q will be equal to, or you can say Q tends to, because I have considered that condition of limiting condition. So we will say Q will tend to Qmy over My plus this My, small my. And so in this condition, what will be the value of a square root of Ey? We have found the expression for root over Ey. So now you can see what is root over Ey. Root over Ey is equal to P plus minus root over P square plus Q. Now in this condition, we have seen that this P tends to 0. So this root Ey will be simply equal to in fact Ey, root over Ey. So you can say that as in this condition P is tending towards 0, so this result says that this root over Ey will tend to root over Q, and so this implies Ey will tend to Q, and hence we can find the value of Ey. Therefore Ey will tend to what? This will be Qmy over Qmy. In fact, here there should be capital Y in subscript 2. So this is Qmy by Qmy plus My. Say this is equation 3. So this is the kinetic energy of the emergent particle when the reaction is exoergic, and we consider that the projectile is of zero kinetic energy, that is, the projectile has no kinetic energy. In this condition, the kinetic energy of the emergent particle is equal to qmy over my plus my. You can see from this result that the kinetic energy of the emergent particle, that is this Ey, is independent of theta. Here there is not a cos theta term, so you can say this result is completely independent of theta. And when you say that this is independent of theta, what does it mean? It means the value of Ey will be same in all directions when the kinetic energy of the projectile is 0. So you can say that this Ey is not equal to a function of theta, and so this implies Ey has same value in all directions. So this is the kinetic energy of the emergent particle when we consider that the projectile is of zero kinetic energy. So you can see this is a very remarkable fact that an exoergic reaction may be initiated even when the projectile has no kinetic energy. This is the remarkable fact, because we will see in case of endoergic reaction this is not possible. An endoergic reaction will not proceed when we take Ex equal to 0. But an exoergic reaction may take place even when the projectile has zero kinetic energy. Now we will consider the another case, and that is the finite and kinetic energy of the projectile. So now let us see what will be the result when the projectile has a finite kinetic energy. So finite projectile energy. Finite projectile energy. We will now consider this case. Now we have defined the value of Q, and you have seen that we have defined Q as follows. How we have defined Q? You can see Q has been defined in this way. This is equal to Q into capital My plus My minus Mx into Ex over My plus My. This is actually how we have defined Q. Now, since in all nuclear reactions the rest mass of the recoil nucleus, that is this capital My, is definitely greater than the rest mass of the incident particle, that is this Mx. You can say, in fact, this My is definitely greater than this Mx, always. In all types of nuclear reaction, this is possible. My, that is mass of the recoiling nucleus, which is capital My, is definitely greater than the mass of the projectile. So you can see this holds actually in all types of nuclear reaction. And since My is greater than Mx, so My minus Mx will be positive. So you can say this my minus mx, this will be actually greater than 0, and when you say greater than 0, it means it is positive. And if it is positive, then you can see all other terms in this equation defining the value of q is positive. So in this case, this small q will definitely have a positive value for all values of Ex. Ex is kinetic energy, which is never negative. So when Ex has any positive value, then this q will be positive. And so you can say q is positive for all values of Ex. This will be positive. And so as we have seen that the quadratic equation in root Ey has two roots, but in this condition, since q has always a positive value for all values of Ex, so in this condition there will be only one root of that quadratic equation which will be in fact acceptable, and that root must be in fact the root taking after the positive sign. So you can say therefore there will be only one acceptable root of the q value equation. And that is, what is in fact that root which will be accepted in this case? So that will be actually root over Ey equal to p plus, we have dropped the negative sign because in this condition only one root will be possible, and that is positive root, and so this will be p plus root over p square plus q. So you can see in this case Ey is a single valued for all possible values of the incident particle energy Ex, and this value is given here. So in this case Ey is single valued for all possible values of the incident particle energy. That is Ex. Incident particle energy is Ex, and it is given as, and it is, this is simply root over Ey equal to p plus root over p square plus q. Now you can see from the values of p and q, we have mentioned the values of p and q, or you can see the original quadratic equation here and decide the value of Ey will be what in accordance with the different values of theta. So you can see it here. You can see this root EY. This is at the place of P, and this is P square, and this is Q. You can see the term for P contains actually cos theta, and you know when theta will be 180 degree, then cos theta will be minimum, and it is -1. Here there is actually cos square theta, so when theta will be 180 degree, then cos square theta will be +1, which is its maximum value. So actually when cos theta will be minimum, that is -1, then the value of root EY will be minimum. So you can say that in this case the kinetic energy of the emergent particle depends on theta, that is a function of theta, and it will have the smallest value when theta is equal to 180 degree. It means the emergent particle emerges just in the backward direction. In that condition, its kinetic energy will have a least value. So in this case, you can see in this case, this EY is actually a function of theta, and when theta is equal to 180 degree, then this cos theta will be equal to -1, which is its minimum value, and so EY is minimum when theta equal to 180 degree. And what does it mean? It means actually here is actually our nucleus, let us say capital X. The projectile small x hits this target nucleus, and after the strike, the emergent particle emerges in a direction just opposite to the direction of the incident particle. So in this condition, when the particle emerges in backward direction, then its kinetic energy will be actually minimum. So this is the energetics of the exoergic reaction. Now we will see the endoergic reactions energetic, but in second lecture.